right, so we're going to start with number 10. It's about our modified outlet machine, which is good because this is what our lab is on whatever day it is. Tuesday next week, we're going to do a lab on a modified outlet machine, just like this one. So, acceleration of the hanging mass, tension in the cord. They give us some masses of our objects and no friction and a frictionless pulley and a cord that has no mass. All sorts of nice fun stuff so that it doesn't have to. Now remember, how many force diagrams do I need to get full credit on this one? 3. Did you get system? Right, and the one for the M1 and one for M2. So 3 diagrams to get full credit. The system, you would do, let's see, I'm going to put my dotted line here around my system. And it's going to accelerate in this curved direction. It's going to have the weight of number 2 here. I'm actually going to use green for these since they're a different direction. The weight, there. The weight of number 1 here and the normal force of number 1 here. That would be for my system, doing block number 1. And over here we'll do number 2. Let's see. Mass of 1 is 37.3. So I'm going to write that in here. Just to make my life easier. And the mass of number 2, 16.2. Okay. So that means the inertia of my system is 53.5 kilograms. Right? Okay. So here I've got FG2 and a tension. Here I'd have a tension. That would, and then in the perpendicular direction I'd have FG1 and FN1. And then each of those would have acceleration. Remember, all the blue arrows are in one dimension. The acceleration points in that same direction, and then the green arrows are in a perpendicular dimension. All right? Because we have this weird going around the corner thing, so we kind of have to stretch out. You could even draw the force. Well, when you get to free body, all that's important really is the relationship, not the whole directionality. Well, the directionality that they're proportional or something. So if I want to find the acceleration, I think it'll be easiest to use the system. Yes, Caitlin? So my masses? Well, it'd be nice too, but I just ran out of room. And trying to draw it big enough so you guys can see it. Alright, so we're going to do the acceleration, which means we're going to use the system. I'm going to use the system. And so, of course, I start off, as always, with my picking out the relevant equation, which nicely, I only have one equation in this whole section, which is that. And then I'm going to fill in that equation. I think I'll first do it graphically. It makes more sense to me. So this is 53.5 kilograms is the inertia there. Going to have the weight of block 2 that way. The weight of block 1 this way, and the normal force of block 1 that way, and the acceleration is that way. So that's filling in that equation graphically with a picture rather than numbers. Does everyone see how I got those and the relationships? Yeah. All right. So I'm interested in the acceleration, so I'm going to try to just look horizontally and see if I can get there, but not even worry about the vertical until after that. So let's see. Now I'm going to take that picture and write it mathematically rather than drawing a picture. I'm going to get FG2, so then I take to the right to be positive, equals my inertia, 53.5 kilograms, times my acceleration. Okay. Oh, wait a minute, I know FG2. That's the weight of block 2. So that would be the mass of block 2 times the gravitational field strength. Right? Because that's the one that's providing that weight. Which in my case is what, 16.2? Yeah. So I have 16.2 kilograms times 9.80 newtons per kilogram, all divided by 53.5 kilograms equals A. Grab my calculator. And I get an A of 2.97 meters per second squared. Good? Alrighty. Let's go, move on down a little bit. So now they want to know what the tension is, and I could use either individual body to find the tension. I think I'll use the mass 2, just because I feel like it. So start with my equation. You okay? Fill it in pictorially. FG2, FT. Oh, did I put T or FT? It should be, I should have put FT here, sorry. F sub T. And it's accelerating this way at, must be the end of the day, I'm doing that. Accelerating this way at 2.97 meters per second squared. So I filled in my equation picture, now filled in with math symbols. I have FT, I'm going to take up as positive, minus FG2 equals M, which is 16.2 kilograms, times a negative 2.97 meters per second squared. How did I know it was negative? Because it's down. You know, in my drawing, I made it point the same way as FG2, so if that's negative, they both are negative. So I get that the force of tension is FG2 minus my 16.2 kilograms times 2.97 meters per second squared. I just brought that negative symbol out front to move my FG2 over. Because it would be FG2 plus 16.2 kilograms times negative, if I brought the negative out front. See the negative? Went from there to up. Okay. So FG2 I know from before is 16.2 kilograms times 9.80 newtons per kilogram. What? Okay. Minus 16.2 kilograms times 2.97 meters per second squared. And I get a tension of tension of 111 newtons. Yay. All right, so number 7. All right, we got the superhero and the sidekick hanging, all that fun stuff. How many force diagrams? 3. So, for the system, which would be both of them together, let's see, we would have the total weight down and tension 1 up, let's call it. So then on the end, and no acceleration, right? This is number 7. So then you'd have FT1 here. You would have FT2, but you'd also have the weight of the superhero. We'll call him Green Man. Green Man. Okay, that's your job. It wasn't Batman's, I changed one note. His sidekick, good old Yellow Boy. Fine. Good old Orange Boy. You're welcome. So, let's see, the superhero's Green Man's is 91 kilograms. So, 91.0 kilograms. Force of gravity, so the weight of Green Man, G. And then, well, it says the superhero hangs and with the trusty sidekick hanging below him. And Orange Boy is 53.5 kilograms. So that means the system has an inertia of 144.5 kilograms. Right? Now, you don't have to write those masses in, but it might be helpful. And so they want to know the two tensions, right? Yep. Which one do you want to do first? The tension number 1 or the tension number 2? Okay, we had 1 vote for each tension. Anthony, break the tie. Break the tie. Paris, break the tie. 2. Okay, so we're going to do tension number 2. So I'm going to use Orange Boy to do it. Alright, so I'm going to start with my equation. Sum of the forces equals MA. Why do I have to start with that equation? That's the only equation we have. It is, and you'll look back at this and go, oh, remember the days when we only had one equation? You will, trust me. So the weight of Orange Boy is down, force of tension 2 is up, and he has an inertia of 53.5 kilograms. So, now putting that in, I get FT2 minus the weight of Orange Boy equals his mass. Whoops, I know that. 53.5 kilograms times the acceleration 0. So FT2 equals the weight of Orange Boy to be 53.5 kilograms times 9.80 newtons per kilogram, and I run out of room. That's the weight, yeah. Yeah, the weight, another way to say weight is the force of gravity. In fact, it's kind of a better way. They made up the word weight when they didn't know what it was. Huh? Oh, that's the, remember, our one of our identities is that F sub G equals M little g. Now, let's do, you guys want to do the system or Green Man? Define FT1. Let's do the system. So if we do the system, $144.5. I decided to give my voice a break for a second. Yeah, it's basically, because, I mean, look at their free body diagrams. They're like identical except for different masses.